Okay, great. So, hi everyone. My name is Kostas, as Vaso said. I'm very happy to be here. So, thanks for the invitation, and I'm delighted to share with you our exciting work we're doing with galaxy clusters in order to better understand the universe.
Can you switch?
Right. This.
On Zoom, you switch.
Right. Yeah. Switch what?
It's swap displays.
Right.
Upper right, upper left corner. Swap displays.
I did that, but nothing changed. Wait. Wait, hide floating meeting controls. Now it's better.
Stop sharing.
Okay, just a second.
Okay. Now we can screen 2.
Much better after the end of the beginning.
Perfect. Now you can.
Okay, good.
Oh, thank you.
Okay, good.
Sorry.
Okay, thanks. So yeah, as I was saying, I'm delighted to be here and share with you our work with galaxy clusters and cosmology. And before I dive into our results, I will take you through a brief introduction on the standard model of cosmology called Lambda CDM. As I'm sure you all know, for some reason, okay, wait, my slides are not showing properly. Okay, weird. Anyway, so as you know, Lambda CDM tells us that the universe is roughly 14 billion years old. It all started with a Big Bang, where all space, time, and matter were created in a cosmic singularity. After that, the universe exhibited a very brief period of time called inflation, when it grew rapidly, filling space with cosmic radiation, baryonic and dark matter. And as it kept expanding and expanding, it kept cooling down as well. And roughly 400,000 years after the Big Bang, it became so cool that free electrons were captured by protons, forming a neutral hydrogen. And this actually made the universe transparent to photons. So for the first time, photons were free to roam the universe. And this is called recombination. And it's this pretty picture here, which represents the cosmic microwave background, as we call it. And this is actually a little bit important for later on. So keep that in mind. So the cosmic microwave background is the first radiation we can see from the universe. Then after a while, structures began to form, galaxies were formed, stars, planets. The universe kept growing, and roughly 7 gigayears after the Big Bang, or 7 gigayears before today, dark energy started to dominate the expansion. So the expansion started to accelerate, actually, instead of decelerate. And what I want you to remember from here is that there is a parameter, a cosmological parameter called the Hubble constant, H0, which describes the expansion rate of the universe today. Arguably is the most important parameter in modern cosmology, because many of you have heard from the Hubble tension. And it's roughly 70 kilometers per second per megaparsec. The units might sound weird. It's velocity over distance. But this is not important. The important thing is to remember that H0, which is the parameter we will focus on this talk, describes the expansion rate of the universe. Now, as the universe expands, galaxies recede from each other, right? And photons that are emitted from these galaxies travel through an expanding space-time in order to reach us. Due to the properties of dynamical space-time, what happens is that we observe these photons with lower frequencies than the ones they were emitted with. And this phenomenon is called redshift. And we can actually measure this redshift quite easily, I would say, in many wavelengths and for most extragalactic objects. But because, again, a problem with my slides, I don't know what's going on, but okay. but because the further a galaxy is, the more time a photon is spending traveling through this expanding space-time, the more redshifted it is. In other words, redshift is a proxy of distance. The larger the redshift, the larger the distance to the emitter we are observing. Now, let me tell you a few things about the cosmological principle. The cosmological principle is a fundamental building block of lambda CDM, and it postulates that the universe must be isotropic and homogeneous over sufficiently large cosmic scales. This is a very, very strong assumption. So do we have any evidence for that? Well, this picture is from the recombination era, I told you before, the CMB, cosmic microwave background. And we found out that there is a rest frame in which this very early cosmic radiation is highly isotropic, right? So after we make a few corrections about our own peculiar motion in the universe, the solar system's motion, we see that there is a rest frame that is very, very isotropic in the very early universe. Now, the core assumption is that of lambda CDM is that matter in the late universe, galaxies, supernova, other things, should converge to an isotropic behavior after a certain scale, which is 150 megaparsecs, or if we like 500 million light years. They should converge to an isotropic behavior in the rest frame of this cosmic radiation. So let me repeat. The core assumption of lambda CDM and the cosmological principle is that galaxies and other stuff, the cosmic matter today, should have the same rest frame as the cosmic radiation in the very early universe. This is again a strong assumption. So we have to test it observationally, right? And how we do it? A very simple way is to measure the expansion rate of the universe towards different directions and see if it looks isotropic within the rest frame of this radiation here. So if I measure the H naught up, down, left, and right, and I see that it gives me pretty much the same value, then the cosmological principle holds, and lambda CDM seems to be correct. If it doesn't, though, then we have to investigate why. You may ask, okay, haven't people checked that already? Well, yes and no. Until very recently, we didn't have good enough data sets to robustly test.
Are you at all?
Yes.
Can you switch?
Switch to what? No.
Do you have Ethernet? Because it says an Ethernet cable there.
I need an adapter for Ethernet.
I think the algorithm has this firewall where that's the
Okay. Sorry? Okay, should I continue then or wait for? Yes. Okay. So yeah, let's hope it doesn't drop again. But yeah, as I was saying, we don't have robust results on this, or we didn't have robust results on this until a few years ago. Now, we came up with a way, use galaxy clusters, to really and very powerfully test this assumption of the cosmological principle isotropy. So let me tell you a few things about what galaxy clusters are. In a few words, they are the largest systems in the universe, the largest relaxed gravitationally bound systems in the universe. They have masses up to a quadrillion solar masses and diameters 1 to 5 megaparsecs, right? So wherever you see megaparsec, you can multiply it by 3 and it gives you light years. So galaxy clusters are formed due to this process of large-scale structure formation. So initially, the matter distribution in the universe was very smooth, with small primordial density fluctuations, that due to their self-gravity and given time, they grew and grew and grew. So yeah, it keeps giving me this problem with the slide. I don't know why, but anyway. So eventually, they grew into large structures of the universe. You see that there are some filaments here of matter, there are seeds, there are voids, so no matter at all. There are knots. So at these knots, at the intersections of these filaments, is where galaxy clusters are formed. So they are formed at the densest parts of the cosmos. Did I try? Will you kick me out again now? I think that okay. There are several reasons why galaxy clusters are ideal for isotropy tests. Arguably, the most important one is that they cover the full sky uniformly. Because they are constant emitters, they are always there with the same luminosity, right? We can observe them whenever we like, and we can scan the full sky to detect them, measure their properties. This is not true for other cosmological probes, which require different strategies to be observed. Another crucial advantage is that galaxy clusters cover a wide range of cosmic distances, from our very local cosmic neighborhood up to billions of light years away, as you can see here, for example. In the x-axis, you will see the distance of a cluster. On the y-axis, you will see its mass from two very recent cluster catalogs observed in the X-rays and in millimeter wavelengths. So yeah, they're everywhere. And this means we can study the isotropy of the universe towards different directions and for different cosmic scales as well, which is a huge advantage. And there is no other cosmological probe that can do that right now. In the near future, in a few years from now, there will be other probes, but for now, it's only galaxy clusters. Now, galaxy clusters contain three things. Galaxies, of course, up to thousands of them, vast amounts of dark matter, and the most interesting component for us, hot ionized gas with temperatures of up to 100 million kelvins. And this gas accounts for 10 to 15% of the total mass. So most of the mass is in the form of dark matter. This gas consists mostly of free electrons and protons, and it can be detected in X-rays and microwaves. In X-rays, it can be detected through the brainstorm emission, so free radiation, right? A free electron and a free proton interact, and they emit a photon with X-ray energies of 0.1 to 10 keV or so. So pointing our X-ray telescopes towards galaxy clusters, we can measure their luminosity, right, their brightness. We can measure the mass of their gas. We can measure their radius and other properties. What you need to remember from this is that all of these properties depend on the cluster's distance, right? Because we are here from Earth, we measure angle, we measure flux, we don't measure the intrinsic cluster properties. To derive them, we need the cluster's distance. And the cluster's distance depends on the expansion rate, on the Hubble constant, h0. So all in all of these properties depend on h0. I change the h0, these properties will change as well. So they are cosmology dependent. In microwaves, galaxy clusters can be detected through the so-called Zhunev-Zeldovich effect. So what happens here is CMB photons, so cosmic radiation photons, travel through galaxy clusters. They get an energy kick from free electrons in the gas through an inverse Compton scattering. So this means that when we observe this radiation towards the position of a galaxy cluster, we see a spectral distortion of the usual spectrum of the CMB. The amplitude of this distortion can tell us a lot of things about the thermal state of the gas because it depends on the pressure of the gas. So by measuring this spectral distortion towards okay.
Now say the sentence.
Now, as I was saying for the people online, to test cosmic isotropy, what we really need is the X-ray temperature of clusters, and I will say why now. So what we can do is extract the X-ray spectrum of clusters, which means how many photons we get as a function of energy. We can fit the appropriate thermal emission models for ideal gas plus some metals in order to derive the temperature of these clusters, because you see that the spectrum is very, very sensitive on the high end on the temperature of the gas. And through this process of measuring the temperature, cosmology enters nowhere. So it really doesn't matter in what universe we live in, we will measure the same temperature every time for galaxy clusters. And this is the key here. What we can do is exploit scaling relations between the temperature, which doesn't depend on cosmology, and other properties that do depend on cosmology. We can decompose them, so separate them into observables and intrinsic cluster properties that depend on baryonic physics and cosmological parameters. We can measure all of that stuff on the right hand, so we can determine the stuff on the left hand of the equation. So it's as simple as that. And doing so for different parts of the sky, right, for different patches of the sky, we can get H0 constraints in different directions. We then compare them and see if they are statistically the same or if they vary. It's as simple as that. And one can play the same game with whatever scaling relation you like, because there is always a residual cosmology dependence on the equation here. Sometimes this is 3, sometimes it's 0.5, but there was always something. This means you can use different scaling relations to cross-check your results, which is extremely important in our case. Now, to apply the exact same, this method that I described, we built a cluster sample from scratch. We obtained high-quality deep observations in X-ray, in millimeter, and infrared. We measured a bunch of stuff for clusters that I'm not going to bore you with. You will see them later. And we built 10 scaling relations. You can check these 3 papers for details. And what's also important is that the median distance of these clusters is 800 megaparsec. So let's say 1 gigaparsec, which is kind of local. Not exactly, but kind of local in terms of cosmology. We will focus on these 2 scaling relations because they are the most informative ones. luminosity temperature and thermal energy versus temperature. So as you see these relations, if the cosmology changes, these relations will shift up and down, not right and left at all, because the temperature is not affected by cosmological changes, but the y-axis properties are affected. So if H0 changes in different directions, these relations will shift up and down. And we can actually determine that in order to understand if the universe is isotropic or not. When we do that with these two relations, we obtain these two maps. So different colors here represent the expansion rate of the universe in different directions of the sky, right? So we see a 9% dipole anisotropy in this relation and 13% in this relation, 3 sigma and 4 sigma statistical significance. But what's important here is that these are nearly independent results. So there is no obvious reason why this should match if there is no underlying effect causing this behavior. So the correlation between these two maps is extremely minimal. To visualize things a little bit better, we built the first Hubble diagram of galaxy clusters. A Hubble diagram is the distance, the cosmic distance of an object as a function of its redshift, this change in the frequency of received photons we talked about earlier. As you can see here, the blue points that come out of these blue regions here in the sky are systematically higher than the red points, which means that for the same redshift, we have different distances. This can be interpreted as that we have different H0 values, different expansion rate values towards these directions here. Right, so again, this thing with a slide. Okay, so what we did, and that's the main result of our previous papers, is to throw everything together. Okay, we stack all the independent maps we had of H0 across the full electromagnetic spectrum, almost. And we also combined with other cluster samples, independent ones, completely other clusters. We stacked everything together and we derived the first ever multi-wavelength H0 map, which looks something like that. So you see here that we got a dipole in the expansion rate anisotropy at the significance of 5 plus sigma. This might seem a lot, but you can think that we have independent data, independent samples, but they all show the same behavior. So when we stack them together, it's only natural and expected to get a large statistical significance. This is still, to date, the most robust detection of an anisotropy in the expansion rate of the universe in low redshifts, so in the late universe. We were lucky to draw a lot of media attention. So ESA, NASA issued press releases on our results. Scientific American even made us their cover page. So this drew a lot of attention from the community and a lot of follow-up studies, as you'll see later on. However, I don't want to confuse you. So this 5 sigma signal is not the tension with lambda CDM. Okay. So this 5 sigma thing is the detection significance of the dipole we see. However, in different scales, lambda CDM might allow for some variation in the apparent expansion rate. Okay. So in order to determine the tension with lambda CDM, we need to play around with cosmological simulations. Because to give you an example, if we are in the very dense part of the universe, and next to us, it's a very empty part of the universe, we will see a different expansion rate towards this direction rather than the other direction. So the so-called cosmic variance, where we are located in the universe, is very important, and we have to quantify this in order to understand what's the real tension with lambda CDM. To do so, we use the Flamingo simulations. They are cosmological simulations, state-of-the-art actually. They are the best actually, hydrodynamic and lambda CDM simulations. They are based at Leiden, where I am. So they were very happy to collaborate with us into testing the cosmic variance in our results and how this would affect the tension with lambda CDM. So these simulations have a great mass resolution. So they have clusters inside them. And for each cluster, we have all the data we used for the real data, all the observables we used for the real data. So we have X-ray information, microwave information, optical, everything. So what we did, actually, a master student of mine, Jay, So what Jay did was to apply exactly the same methodology in the flamingo simulations that we did in the real data. Same data selection, same statistical approach, everything. He created 2,000 light cones of different observers in the simulations. And he saw what kind of an anisotropy we see in a lambda CDM universe that we know is isotropic, okay? And this can tell us if our methodology is robust or not, and what's the real probability of our results emerging in a lambda CDM universe. So long story short, we found that the true tension with lambda CDM is 3.7 sigma, which is intriguing. It doesn't change lambda CDM at this point, but it tells us that we need to look into this direction a lot more, right? But it also told us that our methodology slightly overestimates the apparent anisotropy, because this all should be zero, okay? So now we know what we have to do in order to make our methodology better. And that's why we actually started this project to begin with. But 3.7 sigma, as you know, it's not negligible at all. So follow-up studies. What did they tell us? Do they agree with what we found? There was a study by a group in Sussex University in the UK, where they reanalyzed all of our data and they performed their own analysis, and they found pretty much the same thing. So they confirmed that that these specific clusters, at least, do trace an anisotropic expansion. Also, with another student of mine, Aditya in Bonn, we used independent optical data of clusters, 320 clusters, to study different scaling relations in optical wavelengths. And we saw the same pattern again at a 3.6 sigma, right? Almost independent of what you saw before. Aditya published his paper in A&A last year, and this is a highly exciting result because it tells us that it doesn't really depend on X-rays. The anisotropy is there also on optical. And of course, there is ongoing work with our group where we perform new measurements of galaxy clusters, measuring, for example, their gas mass, in order to build new, better scaling relations. And when we did, we again see the same thing, 3+ sigma dipole anisotropy. So this thing keeps appearing all the time. Arguably, the most important test is the one we did with an X-ray telescope called EROSITA. EROSITA is a collaboration between Germany and Russia, and it's performing the first X-ray all-sky survey in 30 years. It has completely revolutionized X-ray galaxy cluster science. Just to give you an idea, before EROSITA, we roughly knew 2,000 clusters in X-rays. Now, since last year, we know 12,000 clusters. 8,000 of them are new detections in any wavelength. The only pitfall is that EROSITA covers, we have access only on the half of the sky, the German sky, let's say, and the data on the Russian sky are still to be released. Hopefully they will be released in the future. But still, with 12,000 clusters, they're more than enough in order to perform the same tests. And what we found completely dependently is the same pattern again. So same exact region with the same exact H0 anisotropy. This map is 100% independent to everything you saw before, because these clusters are all new X-ray telescope, different team behind the analysis of the clusters, no correlation at all. We still see the same anisotropy. So that's extremely suggestive, actually. We do have serious indications that lambda CDM might not describe the local universe efficiently. But we have to ask ourselves, have we actually proved that the expansion rate is anisotropic? That's not the case. We have to consider what happens if H0 is isotropic, okay? What could cause our data? What could be the reason behind our data? We have to look into other effects in the local universe that could cause such things. And we have to quantify the tension with lambda CDM if we mitigate the problem from an anisotropic expansion to local universe effects, and specifically bulk flows. So what are bulk flows? This is again the cosmic web, okay? The large-scale structure of the universe. There are regions that are more dense than other regions. So if we are located in the middle of a dense region and an empty region, we will be gravitationally attracted towards the dense region. this has nothing to do with cosmic expansion. This is a local effect, and it creates a peculiar velocity of the observer and the emitter as well. This means that the redshift we measure is not only due to the cosmological expansion, it's also due to Doppler effects due to the peculiar velocities between the emitter and the observer. And this makes us estimate the wrong distance for our cluster and measure wrong cluster properties, which then can create a fake, let's say, cosmic anisotropy. Taking you back to the Hubble diagram I showed you before, now imagine that the shift between blue and red points is not up and down, but it's left and right. So for the same cosmic distance, we have different redshifts this time, rather than the other way around. And this is what the bulk flow would cause. This is still a cosmological effect, though, because lambda CDM has strong constraints, strong predictions of how bulk flows should look in the universe. And long story short, when we performed the first measurements of bulk flows at such large cosmic distances, we found a 4 sigma tension with lambda CDM. So again, my slides, okay. So this is what lambda CDM allows for bulk flows. These are different realizations and simulations. This is our result over here. So this is a 4 sigma tension. So now it's either an anisotropy at the expansion rate or a huge bulk flow in the local universe, both of them equally problematic from lambda CDM. The first one contradicts cosmic isotropy. The bulk flows contradict cosmic homogeneity because they would require huge inhomogeneities in the matter distribution in order to explain them. This means that we have to do a better job mapping the matter distribution in the local universe in order to understand how such huge flow motions might emerge. And that's actually what we try to do in another project we are running. We are trying to find the mass in filaments in the local universe in order to understand if these flow motions can be explained due to gravity. And this is just a parenthesis in the isotropy presentation. Just want to show you this. It's a paper that will be submitted tomorrow or Monday, the latest. And we will have a press release on April because we detected the first ever pure emission from a filament between galaxy clusters in the Shapley supercluster, which we measured that there was hidden mass, let's say, between these clusters of another cluster practically, so 2 times 10 to the 14. This means that the mass of the Shapley supercluster and other structures are underestimated because these filaments were not detected in the past. We make the first detection here, and this could kind of alleviate, that kind of explain our bulk flow, not entirely, but again, it's in a 4 sigma tension with lambda CDM. Now, I want to believe that our best chance of actually figuring out what's going on is a large observational program we got granted this past December 2024 with XMM Newton. So XMM Newton is the most useful, arguably, the most useful X-ray telescope to date. It was launched by ESA, European Space Agency, in 1999. It has costed more than €1 billion up to now. And it's still the only X-ray telescope with large field of view and high spectroscopic and imaging resolution and deep exposures. So it's extremely useful. And this is the telescope on which our work has been based until now. So we got a 0.5 megaseconds large program. This is roughly 140 hours to do this. So we'll observe 40 clusters in the very heart of the cosmic dipole direction here. And we have predicted that this will lead to either a 6 sigma detection of the dipole, then we know it's there, that's the end of it. Or if it's not there, which I highly doubt it, to be honest, we'll completely dispute it. So this will be very conclusive for the cosmic isotropy studies. And we expect the first data to arrive April 2026 until the end of 2026. So this brings me to the last part of the talk, which will be very brief. What we should expect in the future for cosmic isotropy tests with galaxy clusters? Well, a lot of exciting stuff. In X-rays, Rosita has already discovered 8,000 new clusters, right? But in the next few years, it will discover 40,000 new clusters. That's a mind-blowing number to do statistics with, and actually clusters in the distant universe as well. Also, we have another collaboration, international collaboration with University of Athens, University of Lyon, UK universities called X-Class, where we are using the XMM Newton, the telescope I described earlier, to measure the temperature and other properties for very distant clusters in order to see if at the distant universe, this anisotropy thing is still there. In the millimeter wavelengths, there are a bunch of cosmology telescopes, Atacama Cosmology Telescope, and of course the Planck Telescope, that they keep giving us large catalogs in microwaves, in millimeter, that we can exploit in the near future and derive again conclusions on cosmic isotropy. And the elephant in the room, Euclid, which we are actively involved as a group in optical wavelengths, it will discover more than 100,000 massive clusters. That's a number that we couldn't even think about a few years ago. And it will allow us to build optical X-ray scaling relations and to really understand what's going on. And also DESI and the Rubin telescope, they will also give us a lot of galaxy clusters in the very near future. So exciting analysis is on its way. Which brings me to my summary. I hope I convinced you that galaxy clusters are super useful in order to test one of the most fundamental assumptions of lambda CDM, the so-called cosmic isotropy. And when we did so with a novel approach we came up with, we found a 5 sigma dipole in the expansion rate, which is at a 4 sigma tension with lambda CDM, either an expansion rate anisotropy or a huge bulk flow. They are equally problematic for the standard model of cosmology, which might need revision, at least in the lab universe, because there are other tensions as well. And follow-up studies, either by us or by other groups, kept finding the same thing. So the evidence started to pile up that this anisotropy is there. And in the next 5 years, with vast amounts of X-ray data, optical data, millimeter data, we will be able to tell once and for all if lambda CDM needs revision or if it still holds. So thank you.
Costa, questions? Costa.
The main source of uncertainty of measurements are the temperature measurements from the X-rays or the number of objects?
Well, not the statistical uncertainties. The main source of uncertainty is the scatter in the scaling relations. So this is a 30% scatter or so. So we need a lot of data in order to decrease the statistical uncertainty. For now, we still get a 40 degrees uncertainty in the direction, but that's exactly why we try to build new scaling relations with a lower scatter, because that's the key. Reducing the scatter is the key in order to understand, in order to pinpoint better, let's say, the direction of the anisotropy and the amplitude. So this relation, for example, has an 11% scatter on H0, and it can give us better results. So that's the main source of uncertainty, the scatter in the scaling relation.
And what is the origin of the scatter?
The origin of the scatter is baryonic physics in the clusters. So these scaling relations assume that everything is due to gravity. But as you well know, especially in the core of clusters, a lot of baryonic stuff are going on, AGNs, turbulence. So the scatter depends on the relaxation state of the cluster, on if it has an active galactic nuclei in it, baryonic physics. That's it.
But then, if I may continue, okay. But then if you apply the scaling relation developed based on clean samples of clusters to a random sample of clusters that you observe with Rosita, then you have to screen that sample as well.
Yes.
How do you do that?
Yes.
Because Rosita only gives you a detection, doesn't really give you
exactly
information.
That's why we analyze every data set from different telescopes and different surveys separately. We derive H0 and then we perform a joint likelihood analysis on H0. We don't analyze cluster data sets together because different telescopes have different weaknesses, different selection functions. So as you said, eROSITA will probe a different cluster population than XMM or ROSAT, so we don't mix them up. So it's important, just to conclude, it's important to understand the physics in the clusters as well to do that kind of tests.
So suppose it's there and it's either about motion or H naught is not the same. So what are the implications for lambda code dark matter? What do you have to change? I don't understand.
Well, you have to find a mechanism that could cause, first of all, either an anisotropic expansion. There are models.
So basically, you're missing something.
Yes, yes.
So lambda code could be there. It's just something else.
Yes. Lambda CDM model might be wrong because this assumes that isotropy is there. This doesn't mean that dark energy and dark matter is not there.
Isotropy is there when you look at the microwave pattern, right? It is there.
Yes.
And actually, it's isotropy mind-blowing.
The question is this isotropy in the rest frame of radiation, in the early universe, the same rest frame as today in matter? That's the core assumption here. Isotropy is there for the radiation in the early universe.
Yeah, exactly.
Does this mean that isotropy in the last 14 billion years maintained?
Exactly, so that's what I'm saying. You're missing a mechanism.
Exactly.
Perhaps.
Yes.
So, the lambda CDM from the Planck data is there.
Yes.
Based on the analysis of the microwave background radiation, right? Yeah.
Not necessarily. So from the Planck data, we know isotropy in radiation is there. The fit,
And matter as well, because they were.
dark matter, of course, is there. Yes.
It's not just radiation, it's matter as well. At that time,
Yeah.
matter is unit, like all over the place.
Of course, yes. Yes, we are wondering if there is something happened, if something happened in the last 14 billion years. Exactly. Yeah. Yes.
But to add on that, like, see, there are indications for anisotropies on the CMB as well.
Yes.
In low wells. So this is very low well. This is the type.
Yes.
So on the CMB, there is an actually correlation between the dipole, the quadruple, the octuple, called axis B.
That's because you have one unit. That's.
No, but you cannot really, yeah, well, you can sweep under the rug, anything, and say, it's cosmic variance.
Yes, it is.
But it's very suspicious because this is not off from the CMB axis of review. They are kind of aligned, which is very weird.
You don't measure an isotope direction of CMB.
They do, that's what I'm saying.
On that direction.
Yes, or roughly the same direction. Do you have
Yeah.
There.
So there are other indications. So CMB is somewhere here, the dipole, somewhere here. So the thing is, as Kostas said, that we have cosmic variance. We can always have cosmic variance. This means, though, we live in a special place in the universe. Yes. But this is opposite to what lambda CDM assumes, that we are Copernican observers in a very average place in the universe, which is not the case. And then every cosmological application, every cosmological study assumes everything is the same everywhere, which means that they assume we are average observers. Either we are not average observers and CMB indicates isotropy, or CMB indicates anisotropy and we are Copernican observers. So it's kind of correlated.
If I understand correctly, the future measurements you're going to do at a different version.
Yes. Yes, that's exactly the point. Yes.
Is there expected how you're going to divide the versions? What do you think you're going to?
Yes. So when we do this test in 2-3 years from now, 4 years from now, at high redshifts, what happens? We are here somewhere, let's say 0.4, even higher. Then you cannot have a bulk flow to explain that stuff. Bulk flow would be tens of thousands of kilometers per second. That's unfeasible. So if the anisotropy is there at high redshifts, that's a universal phenomenon. If it's not there, then it's a local universe effect, and we should look into the homogeneity of the local universe. So by looking at high redshifts, we will be able to tell if it's a bulk flow or it's not an anisotropy we see, And then we have to consider modifications accordingly to lambda CDM to understand what's going on. But people have tested that actually. I have a backup slide on that, if I may. So here, for example, come on, where there is the citation? This paper and the paper from the same authors 1 year ago, they used quasars in the very distant universe, redshift 1, you know, and they did find a 5+ sigma dipole anisotropy, which in other words, it means that the rest frame of distant quasars, the rest frame of matter, is not the same rest frame as the CMB, even at high redshifts. So you see here but the direction is the same, as Kostas was saying. That's mind-blowing. There's no obvious reason why the direction should be the same. But we see that the two rest frames, matter and radiation, are not the same, according to this paper at least. So we will be able to tell with clusters as well in the near future.
Elias has a question online.
Go ahead, Ilya. Yeah, you're muted.
You're muted, Ilya.
Yes, I do have a couple of questions. Sorry, but they are a bit basic. First of all, why the gas in the middle of clusters has such high energy? Where does it come from?
It's a virial equilibrium because of the mass of clusters. Well, the gas just falls into the gravitational well of clusters.
So it's
And
gravitational energy, you're saying?
Sorry?
So it's gravitational energy?
Yes, exactly. Yes, yes.
I see. And of course, in order to be virialized, that means that it had time to do so.
Yes.
Is that well understood?
Yes, it is. It is.
Correct?
So the relaxation time of clusters is roughly 1 billion years. So 90+% of clusters had more than enough time in order to relax.
I see.
However, there are objects that are currently merging. There are merging of clusters, which kind of disrupts the whole thing. And these clusters are dynamically all over the place. So we take them out of our sample, and we only consider relaxed clusters that we know they should obey scaling relations rather than.
And why do you get scaling relations?
Well, because if a cluster is larger, it's, as you said, it's gravitational energy, right? So the more mass, it means higher gravitational energy, hotter gas. So directly you have higher mass equals hotter gas. High mass also means more electrons, more protons, more free interactions, more emitted photons, higher luminosity. So they are kind of scale with each other.
I understand, but you told us, if I understood correctly, that the powers that are in the scaling laws vary from place to place. Is that correct?
The powers. So I'm not sure what you mean. So
I mean, a scaling relation contains a power, right?
Yeah. The
So,
slope.
and yes, so the exponent of this power, if I understood correctly, is not the same in all cases. Is that correct?
No. It is the same. What varies is the normalization of this relation.
Okay. So it is the same. And
Yes.
this exponent, can it be computed theoretically? Is it known exactly, if you wish?
They can, but they can be computed theoretically only when we consider gravity, and then they are off from the observed slopes, because the observed slopes also depend on baryonic physics. For example, the luminosity temperature relation has a slope of 2 theoretically, but we measure 2.5.
Okay.
But we understand why we measure 2.5.
Okay. And since these scaling laws, I guess, are very important in your methods to derive what you're deriving, one should know over how many, let's say, decades these are valid, because as we all know, to apply these scaling laws and try to get data, it is very important that they are valid over many decades in order to avoid important errors. So is that well understood? It
is quite well understood, yes. So
the data, in fact, over how many decades they vary in temperature or whatever, in whatever scales?
Again, hundreds of millions of years. So when in our lifetimes, a cluster will not vary. So
no, I understand. But in the relation that you are trying to apply your method, you have a scaling law, and the parameter or the variable in the scaling law sort of varies over a specific range. How big is that range?
Well, once they're relaxed, they obey a law we call a self-similar law, so that all clusters pretty much behave the same once they are relaxed. So it doesn't really matter at what state they are.
No, I understand that, but your data, you're using data eventually, right?
Right, yes.
This particular variable, over how many decades does it vary in your data?
But decades means
Decades means, I mean, powers of 10.
okay. Well, right, yeah. Well, one order of magnitude or so. So from 1 keV,
I see.
keV or so, yeah.
But
so.
in such cases, it's well known that it's very difficult to use scaling relations without doing important errors. And the question is, how can you really substantiate small errors in this analysis?
There are two things that might cause variation between low mass clusters with low temperature and high mass clusters. One of them is the effect of baryonic physics. At low mass clusters, they are stronger. So this creates more scatter than the high-end part. So what we do is we fit a variable scatter, which depends on the cluster's mass, to describe our data the best. And the other thing is that they might change the slope as well. So here, for example, you see indications of a change of a more steep slope. So what we do is we allow for a broken power law as well for cluster scaling relations. And we see if it fits the data better than single power laws, but we don't see that. We see that all clusters at the mass scale we are considering here, 1 to 10 keV, so 10 to the 14, 10 to the 15 solar masses, they obey the same scaling laws. And of course, we do all that stuff, all the astrophysics stuff prior of doing any cosmological analysis, right? So blindly, we make sure we understand the astrophysics of it, and then we try to derive cosmological conclusions. But we haven't seen anything, even in simulations or in real data, that worry us particularly, to be honest.
Okay. Subir Sarkar and collaborators have been arguing along similar lines as you for about 15 years now, but are they looking at the same type of data or they're looking at completely different data?
They're looking at, well, they used to look at supernovae, so pretty much similar cosmic scales, but supernovae are not the best for such tests because they don't cover the full sky. As you can see here, these are the very latest catalogs. Subir, which I know very well, they used to use catalogs with half of this data, so they don't really trace the full sky, but they still found anisotropies. But this result I showed from with quasars, this is Subir's team. So they are the ones behind this 5 sigma dipole anisotropy with quasars. So we're actually tried to work together in the past. Subir is very strong in his beliefs, I think, about what it's there. We're a little bit more conservative. We don't want to prove anything. We just want to find out the truth behind what's going on. But Subir is extremely excited about the anisotropy we find. But yeah.
Okay, thank you.
Yeah, just this, the anisotropy here, is it the same location as you find?
Yes and no. So it's within the 1 sigma uncertainties of our direction, but this anisotropy here is perfectly aligned with the CMB dipole, and we are 40 degrees off. But 1 sigma for us is 45 degrees. However, even if there was an anisotropy where we find it, they couldn't have traced it because they mask a huge part of the sky. Because they cannot use data close to the galactic plane. We can. So, well, it's within 1 sigma, it's 40 degrees. But we trace completely different cosmic scales.
No. The other thing is that the location of your anisotropy, is it very close to where the cold spot is?
Cold spot is minus 60 degrees or so, so it's somewhere here. It's kind of off, yes. I wouldn't expect that Also, the cold spot is a few degrees in the sky, while we find a much larger area in the sky. So I wouldn't think naively that there's a connection between the two. There might be a connection because there is assumptions that the cold spot is indications for a huge void, a super void. Such a void could cause clusters of galaxies to move towards us from this region. We haven't done the math. In principle, there might be a connection. Yeah, my personal opinion is that probably not. But exactly. That's why we're waiting on the future data.
And one last thing, you showed that you detected something like 10 to the 14 solar masses in X-rays.
Yes, let me.
Could this have any implications for missing baryon mass?
Yes, exactly. So, where is it? Oh, here it is. So yeah, I have a small parenthesis here. Well, this project actually started as a way to detect the missing baryons, because for the audience that is not aware of this, we still don't know where 40% of the mass is in the local universe. Simulations tell us that it resides on filaments, but we haven't observed them. That's why we started looking at filaments. But it has two implications. First of all, it kind of solves the missing baryon issue. And second of all, it tells us that there is a lot of more mass close to us that we haven't accounted for to understand this flow motion. So with one shot, two birds, as we say. So, yeah.
Too many. So, okay, can you go to slide 25?
Yeah. Wait. Oh, then this one? Yeah.
Yes. Okay, so you use your scaling relations, right, to isolate this H node at different places in the sky. But and you use the fact that one observable is sensitive to cosmology while the other is not. But cosmology doesn't only mean H node; it also means W.
Yeah.
So what if there is something that changes in the dark energy?
Right. So for the redshift range we cannot explain what we see with omega matter or W variations. So they have to be huge, extreme variations to explain these things. And so it's really not possible to see what we see due to W variation. Doesn't mean that W variation is not there. It means that we cannot trace it at low redshifts. We have to go deeper at cosmic scales in order to be able to trace this. And actually, in the review I have published this year, I go through what kind of observed differences W anisotropy will cause, H naught anisotropy will cause. So one can isolate the two effects efficiently by doing tomography, as Vasilis said. With the data sample we have here, it's only H naught that matters for now.
Anything else? Goes once, goes twice. If there's nothing else, it's time to close the